Hello everyone, I'm Pablo Garrido from Proxima, and today I'm hosting the Embedded Working Group. Please remember to write your name here in attendees in the meeting minutes that I am sharing in the chat. And in order to follow up a bit, in the last session we had Surak from Bosch presenting his master's degree thesis about micro-ROS in AutoSAR. And also we had a presentation by Maria Merlan about how micro-ROS initiative is transitioning from an R&D project to an industry-used software. Okay, and today we have 3 points. The first of them is Piotr Zierhoffer from Antmicro talking about micros with Renode, a tool for emulating MCUs. I think this is a really interesting topic, and now we are going to learn more about it. And then we have our partner at Renesas, Yuuki Okamiya and Kayoko Nemoto, showing us the Turtlebot based robot using the Renesas A6M5 with micro-ROS. And finally, I will talk a little bit about some improvements that we have been doing to micro-ROS in the last month about RCLC parameters and the hard likeness check. So if you are ready, Piotr, we can start. I'll let you share your screen and
okay.
We can start.
Thank you very much. I will allow myself to share the entire screen because I'll have some live demo afterwards. Just let me check everything's okay. Yep. Well, that didn't work out as expected. Right. Loading. Okay, so I guess you should see my screen right now.
Yeah, perfect.
Great. So hello everyone. My name is Piotr Zierhoffer from Antmicro. I'm an engineering manager there. I worked there about 12 years already. Thank you very much for having us here today. And yes, I would like to tell you a little bit about Renode, our simulation framework that we also use to develop our ROS-based applications. Just for an extremely quick intro, Antmicro was founded 2009. We are a company that's oriented around open source. So most of our developments is open source. Renode itself is open source, but we are of course a commercial company. So we're offering services around these tools, and we are mostly software developers. We try to improve the and change the development of embedded systems in general to be more software-oriented and software-centric. And for that, we create new methodologies and workflows all around open source. We work in many different areas, starting from hardware development and, of course, software development. We do a lot of AI, especially edge AI processing. We do cloud development. We introduce new workflows and try to modernize companies to use cloud capabilities to improve their everyday work. And we develop tools, and this will be the main topic of my today's presentation. Why are we even discussing micro-ROS? From our perspective, micro-ROS is very useful when building complex applications that are distributed, very often in the edge AI context, where we create complex setups based on processing nodes that gather data, perform ML processing. And each step of this processing that we create, like video processing, classification, etc., is usually a different node in the micro-ROS or ROS system. We also work with a containerized-based approach where we develop our node that's currently interesting to us in a container-based environment, connecting it to the whole setup, so we don't need to develop and work in complex environments. We try to isolate everything, but we also create simulation environments, and we try to develop things in simulation. We were invited here as I believe prompted by our one of the recent blog posts about debugging micro-ROS applications in Renode. So I invite you to our webpage, and I will also paste the link to the blog in the meeting notes afterwards. So let me start with the quick introduction to what Renode is. Renode is, of course, open source simulation framework for developing of complex systems. We use Renode in the whole development cycle of our projects, starting with hardware development, with architectural exploration, and of course, improving our software development capabilities. We are able to simulate complex systems, but also very simple ones. So the level of complexity and abstraction level that you're focusing on depends totally on you. And we also support not only MCUs, as you were kind to mention, but we also support more complex platforms, Linux capable. We also support FPGA platforms, and we can co-simulate with FPGA payloads, etc. So yeah, as I mentioned, Renode can be used in different complexity levels, starting with architectural exploration when you don't have your hardware or even the proper concept of your hardware yet. You can test and prototype different approaches to the project that you're working on. Then during the hardware development, Renode can also allow you to test different scenarios, different approaches, and allow your software developers to start working on the actual software before the hardware is ready. Yeah, some notable users, some of them you probably recognize, and there's definitely more. We have quite a big community, and we're very proud of it. So how does Renode work? In Renode, you create your simulation based on building blocks. So you, for example, creating a platform, select which CPU or CPUs you'd like to simulate, which blocks you would like to attach to it. For example, this UART, this Ethernet controller, and for example, two I2C buses, etc., etc. And this allows you to create a system that mimics the actual hardware. The goal of Renode is to run the same software as you put on regular hardware, because we simulate the similar blocks. We work on an instruction level from the CPU perspective and on a register level from the peripheral perspective. So we try to simulate the behavior of these building blocks so that the software does not realize that it's actually running in simulation. One of the most important parts of Renode is that we create deterministic test scenarios. So whether you're running on a powerful mainframe or on your laptop, you'll get the same results every time. And Renode can easily integrate with your usual workflows and tools you use on your host, because you can connect the simulation to the host's operating system. This is what the usual platform description file looks like. So this is the fragment of a platform description for Nordics NRF52840. You can see some CPU nodes, you can see interrupt controllers, SPI, GPIOs, etc. The point is that it's text-based, so it can be easily changed in runtime. It can it is relatively readable, and it can be written by hand. And it also can be easily auto-generated, and we do that for Zephyr-based payloads, for Litex, for OpenTitan, and other platforms. We also we not only script the platform description, but we also script the whole interaction with Renode, which I will try to show you in a second. So Renode comes with a CLI that you can write commands into. You have a sample on the right. This sample creates a simple simulation, connects it to a switch, starts some TFTP server, loads some binaries, etc., etc. This can be used for interactive and batch processing, so you can write the script to a file and load it, or you can just type in commands and see what happens. We also have Python support, so you can have more complex logic in your scripting. You can react to specific events, and you can come out with a very dynamic scenario that really allows you to debug and develop your software. Renode is multi-node oriented, so you can also, of course, work with a single platform, but you can connect these platforms via Ethernet, via wireless networks like low power or BLE networks. UARTs, CANs, GPIOs, USB, you name it. You can create very complex setups, and even in such multi-node simulation scenarios, you still have deterministic execution because of the way we handle time progression and message delivery. And the main point about Renode is that we want people to work in CI environments, and we want people to test their software with each and every commit. So you create your simulation locally, you develop your code, and you push it to server. You get results, and of course, if the results are proper, then you merge your code to master, etc., etc. So yeah, this is the what we call the Renode flow that is fairly normal for software developers in large-scale applications. But when talking about embedded systems, when it usually requires some specific hardware rigs to be connected, that's not always the case. And how does ROS and Renode work? So we created this blog post that that I linked to before, and I will link in the notes as well. Renode has always been used by us to develop different types of payloads. Renode is software agnostic, so it can run ROS, it can run Zephyr, it can run bare metal, it can run Linux, or even Android. So there are many different applications, but ROS is especially interesting because of this distributed nature of ROS applications. So with the prototyping capabilities that Renode offers, it was very easy to set up a ROS-oriented simulation. The test sample that we created for this purpose of the blog post consisted of one Zinc platform running Linux and two platforms with ST32F4, as far as I remember. So yeah, what can you do with such a test? You can, with such a setup, you can test each and every node. You can test if they cooperate correctly, if they execute your specific flow. If you have sensors connected, you can verify if they get the proper data, if they form proper messages, etc., etc. So you can test on every scale of abstraction in this context. This is the first iteration that we described on the blog, but it's not the one that I will be showing today. So on our blog, we described the setup where we had two ST nodes running in Renode and connected via UART to the host. There we had ROS agent running and distributing messages, but of course still returning the messages to Renode, making the two emulated nodes communicate with each other. We were working, the blog post is from March, so we were still working on the setup. Right now we have a fully simulated setup with deterministic execution inside, and yeah, more analysis features that I will try to show in a second. So when testing with Renode, you can, as I mentioned, work on different levels of abstractions. So you'll probably start with testing just a very similar, very simple boot flow of your application. You verify if the UART output is okay, etc. Then you will verify if the messages are being sent. For example, if there's a specific sensor input and if there's a certain trigger happening. And this still can be done in a single node environment, but the test will be more complex, more difficult. And in the end, you will want to test the full flow of the complex setup when nodes are exchanging messages. For testing, we use Robot Framework. Robot Framework is a Python-based framework that exposes some kind of a natural language, more or less English. It allows you to use specific keywords that we define and exposes the whole CLI that we have and all the capabilities and more. It allows you to, for example, wait for a thing to happen on UART. It can wait for something to happen on your network, for example, a packet with specific content. You can even wait for specific events that are fully custom and you program them with Python. You can wait for frame buffer, frames, etc. And after the whole test, you get a full report, what went wrong, what went right, which keywords failed, which keywords passed, etc. This is pretty useful. We provide keywords that are Renode specific, but the framework is generic. Yeah, so let me jump to the demo. So I already started something. Here I have, yeah, so this is Renode. Renode is a CLI-based tool and API-oriented tool, so we don't have a fancy UI, but I hope it's relatively visible. I can probably increase the font. Yeah, this is the main entry point for Renode. So let me start, and here we see two UART windows for the Zinc platform, which will have the binary protocol all running there. So let me start with the first STM. You see that device ID is being displayed. You see the protocol data. Let's start the second instance. And in a second, you will see that the nodes are exchanging messages. Hopefully, it's been running for quite some time, but I hope they will send the message. Oh, yeah. I thought that the demo effect kicked in. So yeah, you'll see that the messages are being sent, they are being received. You see that the IDs of the nodes are actually visible in the recipients. You also see that they get their own messages because we broadcast, we're subscribed to the same topic in both applications. So yeah, this is like a very simple scenario, but of course it allows you to do a lot of testing. You can use Renode for to gather a lot of info about your applications. So for example, you can log all the function names that are running in ROS and are have UART in their name. You can log peripheral access to specific devices. So whenever there's data being exchanged, you will see which registers were accessed and what values were returned, etc. Yeah, so for example, let me pause it. Here you can see that there is some polling going on, and you see that we read the status of the status register of the UART, etc., etc. So I can't in this very short time cover all the debug capabilities and logging capabilities, but you can get the idea that you have the access to each and every detail of the simulation that is going on. Yeah, so you can also connect GDB and debug this multi-node setup easily. This is extremely useful because when connecting GDB and, for example, stepping over the code, our time doesn't flow. So You don't get timeouts on the messages, etc., etc. Everything is fully deterministic and transparent from the perspective of the debugged application as well. Yeah, so this is for an extremely short demo. In the blog, you will see all the instructions to recreate a similar setup if you want. Everything is public, all the scripts, etc. So you can play with it if you want. And the other thing that I wanted to show you, and because I mentioned Zephyr, that we're running this on Zephyr. We are members of the Zephyr project, and we are actually maintainers of the RISC-V platform. And what I wanted to also show you is our Zephyr dashboard. Zephyr dashboard is our attempt to use Renode to generate several samples. I may probably increase the font. So MicroPython, TensorFlow Lite, Philosophers, Shell Module, and Hello World, and build it for all the targets that are available in Zephyr. And you will see that for example, for Hello World, we get 140 almost past targets basing on auto-generated data from device trees that are available in Zephyr. So yeah, one of the ideas is to add a column or maybe yet another dashboard with ROS. We have many payloads that are interesting, and of course, this is what you can do from here. You can even, for example, get the Askinema output from your application. You can get the platform scripts and Renode scripts, just run it locally. You can get all the binaries. So this is a nice CI showing you that you can do this in scale. And if you're working on a product that's actually interested in being scalable to different targets, then I believe that simulation is a really way to go. We will be presenting this at the Zephyr Summit in more detail. Zephyr Developer Summit that's happening in about half a month from now. So yeah, very much invite you to join. Yeah, and we do Renode related services. If you're interested in learning more, we're happy to contact you and provide more details. I hope I did not use too much of my time, and if you have any questions, and sorry for being very brief on the details, but if you have any questions, I'll be happy to answer.
Thank you very much. Very interesting. Does anyone have any question?
Yeah. Hi.
Okay.
Yep. Hi, Peter. Thank you for the presentation. Actually, quite interesting. I'm actually curious. How long did it take for this project to like the demo to actually be running? From designing it to actually having it running.
So it was an intern project. So it was project that allowed our intern to first of all get acquainted with ROS, with Renode, and it also employed several interesting features that were developed in Renode during development of the demo as well. For example, we added virt.io support to Zephyr to be able to use file systems that are stored on your host for easier deployment of new versions of the application. So it's kind of difficult to say, but with the platform support that we already have, if all these things are already in place, it's not really difficult. I mean, running a random application that talks over internet for a platform that we support is usually very easy, and we have quite a broad support for different platforms. If you go to docs.renode.io, we have a list of supported boards, supported peripherals, and this is much shorter than in our Zephyr dashboard when we auto-generate things, but these are platforms that we manually tend to, let's say.
And okay, and this is all supporting only Zephyr?
No. Renode is software agnostic, so
okay.
We can run virtually anything. Of course, we use some payloads for testing, and Zephyr is very often the payload that we run, but it's agnostic.
And then I saw that you use the serial communication from micros that already comes, or did you have to create a
Yes.
custom? Okay.
Yeah. So yeah, these were connected via UART, and we can also connect UART to your host. Create a PTS device that you can connect your applications to. So you can connect to applications that are deployed on your machine.
Okay, that's excellent. And yeah, lastly, could you share the link? You mentioned a blog.
Yes.
With this.
Let me paste it in the notes if that's
Yep.
okay. So after I turn off the screen sharing, I will share all the links that I have in the notes.
Well, thanks. That was it.
Thank you.
Okay, I have to mention that I have playing with the tutorial that they provide, and it's just a matter of half an hour to have a simulated micro-ROS node running in this Renode, talking using a UART to the micro-ROS agent without any modification, and everything is quite impressive. Okay, so let's move to the next talk. Now we have Yuuki-san and Kayoko-san from Renesas Japan, and you can start whenever you want.
Yeah. Hello everyone. My name is Nemoto from Renesas Electronics, and I'm located in Japan. And Okamiya-san is also joining, and maybe Bernd, you are there, or from Germany?
Yeah, I'm here as well.
Okay. We are a global Tiger team to support customer, and thank you for giving us such opportunity today. I'm in charge of our industrial robotics solution in our business development unit, and this time we will soon finalize our micro-ROS solution, POC demo solution, collaborating with our eProshima and our microcontroller, RS605. So we are having strong partnership with working on the promotion for our micro-ROS solution together with eProshima. And today, Okamiya-san will introduce our micro-ROS POC demo solution. And I hope you can get good understanding our solution, and we would appreciate your interest. And then before taking over to Okamiya-san, Beard, do you have any comment?
No,
Can
I don't have
can
any
go to
comment to give you. No.
Okay, so let's move on. Okamiya-san, it's your turn.
Okay. Hi, everyone. I'm Okamiya from Japan, Renesas Electronics. I will share my screen. Can you see my screen? Okay.
Yeah.
Yes.
Okay. Okay, I will explain my Turtlebot3 for a ROS embedded working group. As you may know, we had a press release for robotics application on RA MCU September 2nd, 2021 last year. eProshima produced a micro-ROS on RA. RA means Renesas ARM microcontroller, and officially supported the RA6M5 on micro-ROS, and officially supported the EK embedded kit for RA6M5. But this EK board is basically evaluation board for the RA6M5 CPU board. So we are developing a POC board, a proof of concept, that can control a multiple servo and fear one wire UART and RS485, and supports pub sub communication via Ethernet, USB, and Wi-Fi modules, and a CAN. And it supports wide range supply voltage up to 40 voltage. So it is very dedicated to robots. You may know it's OpenSeer. And this is my Turtlebot. It changes from the OpenSeer to my poke boards. And this is my target. JP177 is a code name, and JP177 poke board enables to run micro-ROS and execute SRAM with the Turtlebot3, and which can be utilized for AGV and robots. Okay, and I will show the some demo for you. Just a moment, and just this is my demo. Thank you. I will share the live demo again, and can you see my? Can you see my? Can you see my Turtlebot? This is my Turtlebot, and yeah, and I'm running the micro-ROS from eProsima, and the POC bot published the IMU message, and so I run a topic echo, and then oh, okay. Yeah. My book published IMU information. Yeah. So many fast. And another one, I'll show the turtle theme, turtle teleop key. This shows the when I push the direction key, and then this window shows the debug log. So I push the button, and then the POC bot subscribe the message from the Raspberry Pi like this. I'm using the UDP via Ethernet, so very quickly the response. Yeah, that's all for today. Thank you for your time to showing my demo.
Thank you very much.
Ah.
Does anyone have any question? Okay, so I'm going to share my screen in order to mention a couple of things in order to finish this embedded working group meeting. First of all, here in the miscellaneous section, you have some information about the Renesas and Neproxima partnership. First of all, you have here in a webinar that we have just uploaded with Maria Merlan talking about the integration of micro-ROS in the RA family of Renesas. And also here you have the support, official micro support for Renesas board provided by Proxima. You have the links here. And finally, I would like to mention a couple of small things that we have been doing in the micro-ROS ecosystem recently. First of all, we have been working in a new implementation of the RCLC parameter server. The things that we have included have been asked by the community, and I think that they are really interesting. For example, we have add support for removing parameters. We have add support for creating new parameters in the micro-ROS parameter server just by setting an previously unknown parameter. You in the micro-ROS CLI you will be asked in the micro-ROS API. I mean, you will be asked if you want to allow the user to create these new parameters, so you can play now with having some defined or undefined states on the parameter set or the parameter server. Of course, you have in the same way that you have in the RCL CPP, in the RCL, you have this configuration variable to allow creating new undeclared parameters. We have modified the callback. Now the callback is more complete. You have more functionality. Here we can see an example. And for example, now you in the on change callback of the parameter server, you will receive the old parameter value, the new parameter value, and some context that you can add to the executor when you provide this callback. With these two new arguments, you can check which was the old value, the new value, and for example, if the ROS2 part is creating a new parameter, the old value will be null. And if the ROS CLI is removing a parameter, you will have this pointer set to null. So you can always know what is happening and return true or false if you want to allow the modifications and all the things. I think that this new callback signature is really interesting. We also have add support for a sort of describe string. So now you can use the ROS CLI in order to ask the information about a certain parameter in the micro-ROS parameter server, and you will have a small string with some information. And finally, we have add a new extra low memory mode. In this mode, the features that are available in the parameter server are reduced. You cannot, for example, set more than one parameter at once, so you have to set them one by one. But on the other hand, the memory consumption, the dynamic and static memory consumption, that the dynamic in the configuration phase and the static memory required by the parameter server will be reduced a lot. For example, we with the normal mode, you have about 12 kilobytes using 7 parameters in an F4, and with the new extremely low memory mode, we can have 4 kilobytes of memory usage. This is really interesting. Here you have an example and some documentation in the micro-ROS web page. You have the new API documented here in micro-ROS Humble. By the way, we are working on the port of micro-ROS to the Humble release, and it will be available the next week. Of course, this RCLC parameter server refactor is going to be included in micro-ROS Humble and rolling, because it is an API break, so we cannot backport it to the Foxy or Galactic release, but you will have it available next week. And the other thing that I want to mention is the new hard liveliness check that is available in micro-ROS, precisely in the micro-ROS middleware, in XRCDDS client and agent. And this is a super interesting feature that has been requested by the community. Here you have more information. You have the couple of links in the meeting minutes, but here you have the discussion that we had with a micro-ROS user, because they were asking us what happened when your micro-ROS node, when your hardware, when your MCU disconnects from the micro-ROS agent. What happened if your board freeze, or your board does not have power supply anymore, or any other case when the micro-ROS node will not be able to continue working. The point is that before, the micro-ROS agent is not able to detect that the micro-ROS client is not connected anymore. So it keeps publishing to the ROS2 graph that a micro-ROS node is available. And this make the false feeling of having nodes, micro-ROS nodes, that are on the data space, but in the actual board they are not running anymore. So with this feature, we can enable the agent to ping the micro-ROS client every certain amount of time. This way, the micro-ROS agent will check if the micro-ROS client is available and is up and running, and if it's not, it will remove the ROS2 entities related to this micro-ROS node. This can be turned on and off, and this can be configured in order to select the period with which the agent will try to check the liveliness of the client. Of course, this is intelligent, so you will not add more messages to the transport channel if the client is, for example, pinging the agent or publishing anything. The agent will check the timestamp of the last XRCDDS message that have received, and in this case, when the client part do not send anything during a certain amount of time, the agent will try to check the status, and if the client does not respond, it will kill all the entities. You have more information here in the pull request, but it's just a matter of enabling a CMake option. You can do it in your Qualcomm Meta file, and just by enabling this CMake argument, the feature will start working. And if you, for example, there is a super basic test where you enable the option, flash the code, and then you disconnect the board. Here you have the timeout. For example, in this case, is like 10 seconds. you disconnect in this sample that I have been talking about. In 10 seconds, the micro-ROS agent will kill all the entities related to the micro-ROS client. So in this case, if you check the ROS2 data space, the ROS2 graph with, for example, ROS2 node list, you will see that the micro-ROS nodes are not available anymore. This is a super interesting feature, and we are planning to make a quick demo in the next embedded working group. And of course, we will be talking in a month about the micro-ROS release for ROS Humble. So if nobody has a question, this was the last part of my intervention. And thank you everyone for coming here. Thank you both of the speakers for contributing with the micro-ROS ecosystem here in the embedded working group. And see you in a month.